This is more or less homework basically. So it's just 20 questions, multiple calculus. Let's just get it done. It's like, it's kind of simple, but yeah, let's just get it done. So first question. So one is length is independent of parameterization. When we say length, it's the arc length we're talking about. To illustrate it, that the length of a smooth space curve does not depend on the parameterization you use to compute it. Calculate the length of one turn of the helix with the following parameterization. Cool. So first is like cosine 4ti plus sine of 4tj. So we want one turn, right? So you are going to like view it from the top, and then the xy plane thing should just match up once again. So when does that happen? Whenever the argument is like, so it's going from 0 to 2 pi. So it's at t equal to 0, then at t equal to pi by 2 this happens. So for a, which is the integration from 0 to pi by 2 of, well, this stuff, so it's just the velocity vector's magnitude, right? Which is like what? So the velocity vector is just negative 4 sine 4t comma 4 cosine 4t comma 4. So the magnitude of that, which is just 4 square root of 1 plus 1, which is 2. So it's just that, right? So it's just that, it's just 4 square root of 2 dt. I suppose, yes, that actually makes sense. Sure. So that's the thing, which is just like what? This is 4 square root 2 pi by 2. So it's like 4 pi by square root of 2. Or you could just do it like this. So just 2 square root of 2 times pi. So the length is going to be 2 square root of 2 times pi. That is the thing. All right. The b part is, so it's just once again the same stuff. So like cosine of t by, so it's exactly the same. Wow. But anyway, it's gonna take the full thing now. So from 0 to 4 pi. 4 pi is when it first reaches 2 pi. So that's cool. So it's like when this is 0 to 4 pi, and then you got this stuff, the derivative of that. It's got half. Half is gonna be the thing. Half square root 2, that times, well, nothing. That's the thing, right? Yeah, sure. Yeah, so half square root 2, which is 1 by square root of 2 dt, and that's like 4 pi by square root of 2, which is 2 square root of 2 pi. So that's the same thing. What about c? C is, so you even need to do this thing. You can see what's happening, right? Take the velocity vector. What's that? It's minus sine t minus cosine t minus 1. So minus 1, take it out. The magnitude of that is 1 in any case. So it's square root of 2. So it's square root of 2, and it's going from minus 2 pi to 0. Yep. Which is what? 2 pi times square root of 2, which is the same thing. All right. Question number 2. Distance along the line. Show that if u is a unit vector, then the arc length parameter along the line r of t equal to, okay, to the point something 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 where t equal to 0 is t itself. Arc length parameter along the line from this point p naught where t equal to 0 is t itself. I mean, this is kind of obvious, isn't it? But still, fine. So your velocity vector, that's just, take the derivative of that with respect to t, so just u. Sure. The magnitude of that is the magnitude of u, which is, well, I mean, it's a unit vector, so just 1 basically, right? So it's just integration of this stuff. So just 1 dt from t equal to 0 to some t, which is, guess what, t. So this is like a bit too basic for my taste. Question 3. Question 3 is find t and kappa for the space curve. This is just boring. But yeah, you just got r equal to, so it's ij something t, and then a cosine h cos t by a. So once again, what's cosine of h? It's just e power of, so cosine h of x is just e power of x plus e power of negative x upon 2. That's the way we define it. So over here it just be something like e power t by a plus e power negative t by a upon 2. We take the derivative of that. Yeah. Oh, well, that times of a. Sure. So okay, this is not what I want. Your r thing is just t comma a by 2 e power t by a plus a by 2 e power negative t by a. Yeah. Now your r dot, that's just 1 comma, this comes on the front, it's just 1, so just 1 by 2 e power t minus 1 by 2 e power negative t. Cool. That's gonna give you your this thing t, so you gotta divide by that, right? It's going to be a lot of, oh no, This is really bad. But anyway, just gotta square this stuff. So sure, just 1 upon square root of 1 plus 1 by 4 of this stuff is 1 by 4 of e power 2t plus e power negative 2t, and then minus 2 times of just 1 by 2. So oh wow, oh we took the 1 by 2 out, didn't we? Just minus 2. Cool. Which would be something like what? 1 upon square root of, it's just 1 by 2, 1 by 2 plus 1 by 4 of this stuff. Hey, that is a nice thing because that just happens to be e power t plus e power negative t squared. Yeah, so it's nice. It's e power t plus e power negative t, and we know it's like positive numbers. That's the only thing possible. Okay, this times all of that, 1 comma, yeah, that's your t. So it's just this quantity. It's can't I like simplify this? I don't think I can. This is probably the best way to be writing it. So e power t plus e power negative t. You know what? Actually, just write this as a denominator. That's probably the better thing to do. So just 1 by 2 e power t minus 1 by 2 e power negative t upon e power t plus e power negative t. That's your t. All right. Now n. To get n, we need to find t dot. It's gonna take a lot of time. Well, what's this guy's derivative? Just one upon that thing squared and then that. So, really, that's the only expression I can give right now. But hey, you have to do what you have to do. So this is just e power t minus e power negative t upon e power t plus e power negative t squared times this stuff. You know what, let's call e power t as something. Let's call that as x, just for the sake of our sanity, and let's call e power negative t as y. And so this would just be like x minus y upon x plus y squared times 1, and then 1 by 2 x minus 1 by 2 y, and then that is supposed to be negative, so it's y minus x actually. Alright, and then plus 0, what is this stuff? It's just 1 by 2 power 2, no, that's sure. So just 1 by 2 x plus 1 by 2 y. Cool. This stuff as well. I think I'm messing up something. Oh yes, I am certainly messing up something. Something really, yeah, that's how it's supposed to be. This is also d by a and d by a. Sure, that makes perfect sense. Oh, that's not good. So it's supposed to be dt upon dt by a. That's what we are trying to find. Yeah, so essentially it's just put that a on the top. So it's a t dot. That's what we're looking for. So it's this stuff. Okay. Okay. This upon x plus y. So you gotta multiply by x plus y. So it's gonna be like x plus y squared over there. So it's 1 by 2 x plus y squared. That upon x plus y squared. Sure. That looks okay. Hey, did I mess up? Oh, I did. I certainly did mess up. So you could have just written it directly as just 1 by 2. Isn't that right? Yeah. You could have written that it as this thing. Awesome. So all in all, what you're saying is like a t dot is just this stuff. I'm thinking, is there a better way to be writing all of this? So we want to be taking the normal vector in any case, right? So it doesn't really matter. This a does not matter. Nothing really matters. So you just think about something that's collinear to that, which would be something like y minus x, comma, just negative of that stuff. So just negative of x minus y squared, or you could just say y minus x squared. It's the same. And never mind. Yeah. And this stuff's gonna like go on there. So just plus half of x plus y squared. Amazing. Hey, we have seen this somewhere. It's just like xy basically. So it's x 2xy. Yeah, that's the thing. So it's this stuff. Okay, what is x and y? Well, oh, that's 1. So this thing is 1. Hey, that's That's nice. Let's see if it actually working out. I mean, is it perpendicular to that? I guess it is actually. Just half of x minus. Oh yeah, it is actually perpendicular. Amazing. So that is your like reduced thing. So with that we can calculate its norm and all that. Okay. So you can have your n. Oh wait, so you also need this t dot for other purposes, right? Oh, how I hate this. Yeah. This upon the velocity, which is this guy's magnitude. Not good. T is this stuff, and so you're gonna have t dot that upon the velocity. The velocity is this guy's magnitude, which is the square root of all that. So you're gonna have x plus y. Okay. I guess it was worth to be putting it like that. Sure. You need to be doing a t dot as a good thing, so that this will be good. First of all, just remove this thing. Just remember, x is e power t by a, y is e power negative t by a. Yeah, remember that and things will be nice. So you've got this r dot, and you also have your t thing. Now a t dot is what you're looking for. So a t dot is just y minus x. So you just take the 1 upon x, so x plus y squared common, then comma, so this would just be like negative of x minus y squared, half of that obviously, and this was like half of x plus y squared, so just 2xy, sure, but xy is just reciprocal, so it's 2, so that's the thing, that's your a t dot. So what you're basically saying is t dot is equal to y minus x, which is e power negative t by a minus e power t by a comma 2 upon a times of e power t by a plus e power negative t by a squared. That's the thing. Okay, that's amazing. So you got t dot. What's kappa? Kappa is just the magnitude of t dot upon the magnitude of the v thing, right? The r dot thing. You already know what magnitude of r dot is. It's this quantity. So dividing by that again would just mean you have a cube, and so it's just like the square and all that stuff. So it's just a square minus 2, that plus 4, that cancels, so it's plus 2. Oh, so what's the square root of that? Sure, it's just e power minus t by a plus e power t by a. Amazing. That cancels with that, so just kappa is just this stuff. It's 1 upon a e power t by a, so t by a plus e power negative t by a squared. Yeah, that's how it is. So that's kappa. I really hope I'm doing this correctly, because if I'm not, well, I have no idea to know how, like, so anyway, I got kappa. What about n? N is just 1 upon kappa t dot. Yeah, so oh well, that just cancels this stuff, so it's just this quantity, e power negative t by a minus e power t by a, what 2. Yeah, I guess that's just how it is, huh? This is magnitude 1. I doubt that. Something isn't quite making sense. Like, yeah, first to be upon the magnitude of that stuff, which is like 1/4 that. Oh, there's also the half over there, so you probably just need to have a 2, but whatever, apart from that, it's not a problem. So, ah, what? What happened? What's r dot? R dot is just 2, and then you got like 2 over there. It's 4, and then. God damn it, what the hell? Minus 2 plus 2 is just 2, and then you got 2, and all that stuff is just the same thing. Why is it squared? Shouldn't it be cube? Oh, it shouldn't be, because that would also be the same thing, right? Yeah, I mean, this is actually perpendicular to that, so it doesn't really matter. Yeah, you literally just have a 2 over there. That's the only difference that you have. Yeah, I mean, it's collinear and all, but that's kappa. N is once again just 1 upon kappa t dot, right? Or am I missing something? What is n? N is t dot upon its magnitude, right? Which is, what is the magnitude of t dot? Kappa is just the magnitude of t dot upon v, so it's just gonna be like kappa times v, so it's just t dot upon kappa v, which is basically like 1 upon kappa dt by ds, magnitude obviously, right? Okay, that makes sense, sure. So it's not just this stuff, you have to multiply kappa with v first. Oh, come on. So v is just like r dot once again, so basically divide by kappa, so you cancel that, and then that upon, you know what, just forget it, just normalize this whole thing. So, right, I mean, why have all that headache when you can just do it? You know what, I'm just gonna write this to sort of 5. Yeah, I mean, that's probably just better. You know, don't go through all that headache, just normalize it right away. So just upon, we know what it's going to be, just negative t by a plus e power t by a. Yeah, that's what n is. All right, so that concludes this question. Question 3 is done. Question 4. Question 4 is, which of the following curves are regular? R of t equal to sine square t, sine square t. This guy's, so just t dot, I mean, that's what we, not t dot, sorry, r dot. That's what we're looking for. That thing is just, oh, that's weird. But never mind, it's just like 2 cosine of t, negative sine, so just negative 2 cosine of t sine of t dt. Well, that dt doesn't really matter. And this thing is just the same thing, negative 2 sine t cosine t. That's weird. Yeah, sure, it's cosine. Oh, it's 1 all the time, isn't it? Yeah, I mean, it is correct. That's correct actually. So this thing is never going to be 0 if this is to be regular. Is it never 0 for negative infinity to infinity? Now there are instances where this is actually 0, right? So this is not regular. So A, no. B is the same curve but with 0 to pi by 2. Well, so this thing is just like negative of, so negative sine 2t and 1 comma 1, right? So when is sine 2t equal to 0? That happens when 2t is n pi, so it will happen at 0 and pi by 2, but that's never going to be happening. So yeah, it is. I guess that's actually correct. Okay, C is t comma cosine h of t. Okay, so find the unit parameterization of the regular curve. Sure, unit parameterization of this curve, huh? Oh, I hate this, but let's just do it. So how do you find the unit parameterization? I really don't want to be doing this. But yeah, so basically the arc length is what you want to parameterize everything in. How do you find arc length? S as a function of t is just the integral of the derivative, the magnitude of that, so just like square root of 2 sine of 2t dt from t equal to 0 to t. Yes. So the arc length is just square root of 2 upon 2 minus cosine of 2t from 0 to t, which is just 1 upon square root of 2, 1 minus cosine of 2t, it's 2 sine square of t, which is square root of 2 sine square of t. Yeah, so that was weird. So, never mind. So that's your arc length. We want to write everything in terms of this. So that's never mind. So just what? R is cosine square t and sine square t. Cosine square is 1 minus sine square, so it's 1 minus s by square root of 2, and this thing is s by square root of 2. That's how it is. Well, you can see that this guy's derivative, so as a function of s, it's just going to be like minus 1 by square root 2, 1 by square root 2 all the time. So yeah, this is going to work. So for C, actually no, for B, the same curve we can be writing like this thing. So what happens at t equal to 0? At t equal to 0, your sine square is like 0, so it just becomes, so your s thing just becomes 0. At pi by 2, your sine square is like 1, so it's just like 1 by square root of 2, right? Yeah, so it's 0 to 1 by square root of 2, not inclusive. R of s, r tilde I should say, that's equal to yeah, that looks okay. Next is C, which is find the unit speed parameterization of the regular curves. Oh, okay, so you also have to see if this thing is irregular. The derivative of that is just 1 comma sine h of t. This is well known that cosine t has sine h t as derivative. So yeah, and sine h of t is, well, it can be positive, negative, or anything really. Well, okay, sorry, this should be 1. So square of that, right? So it's just going to be like 1 plus 1 by 4 e power t square is like 2t minus 2 plus e power negative 2t, which is, so the square root of that essentially just 1 by 2 square root of, yeah, you know the thing, so just cosine h of t. I'll take that out, so just cosine h of t, right? And cosine h of t, it is never 0, which means it's actually regular, right? So this is actually like the magnitude of the velocity, in fact, what we just figured out. Yep. So your arc length is just integration of cosine h of t dt. It's going from t equal to, so you need to have some sort of a point which just put t equal to negative infinity. So it's negative infinity to some t. So just like sine h of t. This is not going good. This isn't going to be going good. I don't know if s equal to negative actually makes sense, but that's probably what I'll have to do. So let's just start with 0. So this will be sine h of t going from 0 to t. So sine h at 0 is 0, sure. So it's just sine h of t in the end. That's the parameterization. S is sine h of t, right? So what is this? It's sine h inverse of t. Sorry, sine h inverse of s, and oh damn, this is just really bad. I don't know what I'm doing. Cosine h of t, huh? So cosine h of t squared plus sine h of t squared, that's equal to, hey, no, it's minus of that, right? Cosine h of t squared minus sine h of t squared, that's equal to 1, right? So sine h of t is like square root of 1 plus sine h of t squared, sure. So which is just 1 upon, so it's just square root of 1 plus s squared. These are the things. Sin h inverse is a crazy equation. Okay, do I really want that? No, I don't. So where is s going from? It's negative infinity to infinity, right? Yeah. At negative infinity, what happens? Well, oh, it's gonna be negative t. So it's gonna explode. It's going to explode to. Oh yeah, oh yeah, sure. So it's negative of negative, positive infinity. It's negative infinity, in fact. At positive infinity, it's once again exploding to infinity. So s is going from negative infinity to infinity. It's all real numbers, and so r tilde of s is this thing. I do not want to solve for sin h inverse. I have done that in the past. It's not fun. Question 5 is where I'm going. What the hell is cissoid? Cissoid of diagonals is a curve whose equation is given by this thing. Write the parameterization of a cissoid as a parameter and show that this is a reparameterization of it. Okay. So the parameter curve for this thing is very easy to write because you're already given r and then this is theta as a function. Sure. So it's just what r vector is equal to sine theta, tan theta, cosine theta, then sine theta, tan theta, sine theta. So that is s square and s cube by c. Right? That's amazing. Yeah. What do we want? Oh, we want to reparameterize this thing. So basically s square should be equal to t square. So you're saying that t equal to s. Just set t equal to s. So that's something like s squared, comma. So you got s squared, like s cube upon square root of 1 minus s squared. This was easy. This was very easy. So yeah. Once again, how do you do reparameterization things? So just like r tilde or t tilde, that's equal to r of what? R of phi of t tilde, right? Okay. So you already got r, so it's like r of so basically phi t tilde should be your what? Your theta. Yes, so phi of t tilde is your theta, where t tilde instead of that you're just gonna put t, right? And instead of phi we'll just put theta. So theta as a function of t, and this is just t over here. So what's theta? Theta is just well, t is the same thing as sine theta, so theta is just sine inverse of t. Yeah, that's okay, I think, because this is in the range of sine inverse. I think they specifically set it like that. Okay, so theta is just that, or you could just say pi. So theta is pi of t equal to this stuff. Right. Yeah, r tilde of t, that's just this stuff, t square, t cube. This is r of theta. That's okay. So yes, it's a parameterization. Next, question 6, which is find the parameterization of the following level curves. What's the level curve? I have forgotten what's the level curve, but these are just conic sections. So what you want to find? Oh, this is very doable. So y square minus x square equal to, oh, that's what sort of tragedy is this? It's just it's just cosine h theta, cosine h t, and sin h t. So clearly, like y square equal to 1 plus x square, well, this is necessarily bigger than 0, or in fact bigger than 1. So your y is always bigger than 1, for sure. And since it's always bigger than 1, well, cosine h of t by the AMGM inequality is always bigger than 1. So this is a good thing. It's bijective and all that. So cool. And sin h of t could be anything. So it's like going from negative infinity to infinity, whatever. But yeah. that kind of solves it. Oh, you also have to have the negative and all that, so how would you parameterize that? That is a good question. I'm messing up somewhere. This is not how it's supposed to be sine h of t. No, cosine h of t, right? But it's y square equal to. So it could be the positive one or the negative one. Which one should I go for? Oh well, that isn't working. No, that does not work. What about secant theta and tan theta? Because secant theta can take sort of like all sorts of values, and tan theta, oh yeah, so you're gonna have two ranges over there, and secant theta can take all sorts of crazy values, so that's okay. But these are not differential functions. Think about it. The derivative of secant theta is like secant theta tan theta, right? So at t equal to 0, you're not problem. Yeah, there's no problem in that. Just a second. Okay, I think something is wrong. It's not. So one of my softwares is not working. Really, this isn't the time. Oh, now it's working. Okay, cool. So what I was saying was, yeah, this is a hard curve to parameterize actually. Huh. What else? Oh, okay, this might work. So y minus x and y plus x is equal to 1, right? So we can just call this thing as a, this thing as b, but then obviously b is just 1 upon a, or let's just call this thing as t, this thing as 1 upon t. So we just have y plus x is equal to 1 upon t, and y minus x is equal to t. So y would just be 1 upon t plus t by 2, and x would just be 1 upon 2 times 1 upon t minus so 1 upon t minus t. Sure. Or you could do the opposite. That's probably better suited. Yeah, that seems the better thing to do. So for sixth question, the first question, what's happening is just have x comma y as half of t minus 1 upon t and half of t plus 1 upon t. Right. Yeah, that's okay. B, that's okayish parameter. Like cosine h and sin h, that's probably where you're going. But now these quantities can actually be negative as well. E power, yeah, that stuff cannot be negative, right? So this is the better thing to do. B is x plus, okay, fine. The same stuff as before. What we can do is go for complex numbers now, right? Or scrap all that. Like why do we even care? Just an ellipse. So just 2 cosine theta, 3 sine theta. That's okay. That's completely fine. Question 7. Right? This is completely fine, right? Yeah, I think so. So the thing is, you have to break the curve at a point and say we exclude the starting and ending points, right? And then this actually works. Or just include the starting point and exclude the ending point, so that there's no repetitions, right? That's important because you want your phi to be bijective. Sorry, so we want your phi to be smooth and bijective. Right. Let's go to question number 7. Let, and also phi inverse. So yeah, let gamma of t equal to e power kt cosine of. Wait. So phi inverse has to be. Oh, what the hell? That's not good. Is your phi inverse actually? Never mind. I'm just gonna go forward. We just wanted parameterization. We don't actually want reparameterization. So sure, let gamma of t with this, where t is in negative infinity and k is a non-zero constant. Show that there is a unique speed, so unit speed parameters for all and s approaches 0 as t tends to plus minus of infinity, and expressed as a function of t. So the sine curve of gamma is just this stuff. Oof. Unique unit speed parameter s on gamma. So reparameterization in s such that for all t s would be bigger than 0 and s approaches 0 as t tends to plus minus infinity. Sure. Hey, that is weird. What do you mean if plus minus? Oh, okay, cool. E power t cosine of this is getting very weird. Unit speed reparameterization. You want to find the arc length. That's the only way. It's from t equal to that to that. E power t cosine t and all that. So it's basically like what? It's doing something like a spiral in motion. So initially it's here and then it's like growing. So as t increases, this is going to be like this, and before that it was going to be like that. Okay, cool. So we can just set this to be the s equal to 0. So yeah, I think at negative infinity is going to 0 in any case, right? So just I think that's okay. That's okay. So firstly, we just figure out the velocity vector. So velocity vector is just the derivative of this thing. I'm going to think of this as complex numbers. So it's just like e power kt plus it, right? So this would just be like k plus I, right? And that times of e power k plus I t. Now, the magnitude of this vector, that's the same thing as the magnitude of this vector, which is just square root of k square plus 1. Right, so, whoa, wait a second, what the hell? Okay, that is legit weird. No, obviously this is wrong. This times of e power kt, because e power it is going to be 1, and this is sure. So basically just integrate this stuff, square root of k square plus 1 e power kt from t equal to negative infinity to something. Let's call that this. So that's an s, right? Yeah. So let's call this t. I don't know, t dash. That's probably the better thing to do. So this would just be square root of k square plus 1 upon k and e power kt from 0 to okay, cool. So just e power kt, because at negative infinity this is like 0. So yeah, so that's what s is. Okay, cool. Yeah, that kind of makes sense. Sure. So s tends to 0 as t tends to plus or minus infinity. Well, if it tends to minus infinity, clearly this thing is 0. Oh, okay. So if k is positive and t tends to negative infinity, then s tends to 0. Yes. That makes sense. Okay. Plus minus k is what the seriously. So if t tends to infinity, then it's not even negative now. Okay. You know that's not gonna work. Something isn't quite right about this. Negative infinity is supposed to be, so if k is positive, this is plus minus, or this should be minus plus, right? So let's just say if it's plus. So if k is bigger than 0, then when t approaches positive infinity, your s is not approaching 0, right? Moreover, you want s to be bigger than 0 all the time. clearly just the arc length. Well, you can't have the arc length being measured from t equal to infinity. That doesn't make sense. So it has to be from negative infinity. That's the only alternative for it to be positive at all times. I'm sure this thing is just opposite of what it should be over here. Okay, then express s as a function of small t. We already did that. Sure. So we have the thing, and oh, you also have to express gamma, right? So gamma bar s, that's like what? So e power kt is just this stuff, right? Yeah. You're gonna deal with a lot of natural logs and stuff. So okay, so t would just be like what? It would be ks upon square root of k square plus 1 natural log of that times of 1 upon k, right? So this will just be like sk upon square root of k square plus 1, and then cosine of t, which is this stuff. So cosine of 1 upon t natural log of ks upon square root of k square plus 1. Wow. Yeah. That's what we're going for, huh? Okay. Comma sine of this stuff. So or you could just write it as cis, because it's cosine I sine, right? Yep. Okay. So that's your thing. Okay, sure. So you expressed s as a function of t. You also can express t as a function of s. What else do you want? Okay. Show that the sine curvature of gamma is 1 upon k times of s. So once again, what's the curvature? Is just dt by ds. So t is just dr upon ds, and then you want dt upon ds, which is like what? So it's just d square r upon ds square. So d square r upon ds square. Yeah. Oh, that would be the unsigned one, right? Okay. So dt upon ds is a tangent vector. I'm just gonna fill that out. So the t thing is just like take a derivative of this whole thing. This is just so bad. Like so many different levels. This is really bad. You know what? I'm just gonna take the derivative of the initial thing and then normalize it. So yeah, your velocity vector was just this stuff divided by its magnitude. So that would be k plus iota upon square root of k square plus 1. That terms of e power iota t. That's what your t vector is. Okay, then you want the derivative of that to get your thing. So okay, so your t dot is, so this is a constant, so it's just iota times k plus iota upon square root of k square plus 1 e power t. That's the thing. Okay, so this upon the velocity, right? So in fact, we just figure out this magnitude first. So just t dot, that's going to be, so this doesn't matter, this actually does matter, right? Yeah. So but in any case, it's just going to be like what? It is 1 already. Something is very wrong about this. Why is this 1? No, this doesn't make sense. It, hey, so oh yeah, actually that does make sense, right? Sure, because it was unit in the end. What the hell? Okay, fine. And divide by the velocity vector's magnitude, so just like this quantity. So your kappa is just e power negative kt upon square root of k square plus 1. Amazing. So now you know what your kappa is. Actually, yeah, so you don't need the magnitude of t dot. You just need like where the t thing is going. So just like k plus I. So we just want the phase of this, don't we? Yeah. So that would be something like t plus, so if you had to write that thing, so just like sine of that and cosine of that, so like 1 and k, so it's tan inverse of 1 upon k, which is some sort of constant, we don't really care, so it's just t basically. So d psi upon dt, that would be t, but then we want ds by dt, so that it would be 1. Yeah, so the sign also follows actually. That's amazing, in fact. So the signed curvature is in fact just e power negative kt upon sort of a square plus 1, which is actually positive. Hey, what's s? S is that stuff. Oh yeah, that's actually ks. Sure, that actually makes sense. This is just 1 upon ks. Huh, amazing. Okay, conversely, describe every curve whose signed curvature as a function of arc length s is 1 upon ks for some non-zero constant k. Well, it's just a translation and rotation of this, right? Yeah. Okay, next. Next question is, let this be a regular plane curve and lambda be a constant. The parallel curve, power lambda, what does that even mean? Lambda be a constant, doesn't matter, it's just something. So it's come of t plus lambda and s of t. Okay, what is an s of t? The normal vector, right? Why is this closing suddenly? I have 17 questions with you, right? Okay, I don't know what's going on with you. Anyway, the parallel curve. Okay, why is this not opening? Screen copy. Yeah, this isn't opening, so guess we'll have to abandon the thing for now. So I'll see you guys in the next video.